Hello everyone and welcome to another video with Special Maths Academy. In this video, we'll be looking at the 22nd problem from the 2024 Special Maths contest, the first round. Before I dive into the video, please don't forget to like, share, comment, and subscribe. And also, we've announced the opening of the registration for the next edition of the Special Maths contest. So please do well to register. Okay, let's go into the question. How many numbers in base 3 between 1 base 3 and 1 million base 3 have each of the digits of the base 3 number system? So 0, 1, or 2. To solve this problem, we're going to use the method of counting in mathematics that's quite popular. So inclusion, exclusion principle. I'm going to leave a link in the comments for those who might be interested in reading more about this. Okay. So, to do this, we have to define some sets. So let S, okay, let me put it this way. So let N0 denote the set of N digits base 3. So don't, pay so much attention to how I'm denoting things here. Okay, so N digit base 3 numbers that have a 0 in them. Define N1 and N2 analogously. Okay. So now we want to find the size of, each of the sets. Okay, so first of all, let's look at what the sets like. So 0, 0, 0 would have been a typical example for this, but of course it's invalid because it starts with 0. So I'll just make it 1, 0, 0. Okay, so this is one example. Can have 1, 2, 0. So these are some kind of things. So if n is 3, okay, so n equals 3. So these are some possibilities. And N1 can have a typical example for N1 be 1, 1, 1. Can have 1, 0, 0, of course. Typical example for N2 is 2, 2, 2. It can have 2, 0, 0, of course. So we want to find what we want to find. We want to find first of all, I want to find let's say n digits base 3 numbers that have each of these. So basically, for that to be possible, it means we'll need N0 intersect N1 intersect. So that's contain all the digits. N2. So we need this. Okay. Now to get this is where inclusion exclusion principle comes in. Okay, so know that N0, N1, so N0 union N1 union N2, this is equal to N0 plus N1 plus N2 minus N0 intersect N1 minus N1 intersect N2 minus N2 intersect N0 plus, so the term we're looking for, N0 intersect N1 intersect n2. Okay, so we need to find each of the terms here. Okay, so I think the easiest term to find here, first of all, is this. So every digit in base 3, in the base 3 number system, either has 0, 1, or 2. Okay, so to find the total number of ways, so this the first digit can be a 1 or a 2, and the other digits can fix them in 3 to the power of n minus 1 ways. So capital letter N. So uh, so it means the first digit can be fixed in 2 ways, the remaining digits can be fixed in 3 to the power of n minus 1. So this is going to be 2 times 3 to the power of n minus 1. Okay. Next, we want to find the size of each of these sets. So for n0, okay, so what we can do, we can first of all count the complement. Okay, so um, so the we can count the number of ways that we can create a digit in the base 3 number system using only ones and twos. Okay, so this can be done in 2 to the power of n ways. Okay, so each space can put each space has 2 choices, right? Yeah, but then we want at least one of them to contain a zero. So only the numbers that have only ones and twos are not in this n0 set. Okay, so it means we have to subtract from the total. Okay, so it means so let me just put it here. The size of n0 is equal to, so the total is, we've already established, is 2 times 3 to the power of n minus 1. But then we remove the ones that comprise of only ones and twos. So there must be at least a 0 there. Okay. And let's discuss n1, the size of n1. So we do something similar. So we remove all the ones that comprise of only zeros and twos. So zeros and twos. Okay. So zeros and twos. How many ways can we create zeros and twos? So the first digit, of course, has to be 2 because we can't start with 0. And then the remaining digits can be fixed in, we have 2 choices for the remaining digits. So 2 to the power of n minus 1. Okay. So it means when we subtract this from the total, so n1 is 2 times 3 to the power of n minus 1. So we subtract the set of digits that don't contain a 1. So they contain only zeros and twos, and we see that this can be, they contain only 0 or twos. And we see that this can be done in, so the first digit can be fixed in 1 way, and the remaining digits can be fixed in 2 to the power of n minus 1 way. So this is just minus 2 to the power of n minus 1. Okay. And of course, this is going to be similar for n2. So just swap the places of 1 and 2. Okay. Next, we have to discuss, the intersections. Okay. So we need to discuss the intersection. So let's look at the intersection. So for instance, n0 intersects n1. Okay. So what kind of digits are in n0 intersect n1? So first of all, we can, apply inclusion exclusion principle again on this smaller level. So basically n0 union n1 is equal to n0 to the size of n0 plus size of n1, okay, minus n0 intersects n1. Okay. So we can do this. We already have this. We have this. This is what we want to find. So I believe it's easier to find the union. So what does the union look like? So union looks like digits that contain, so each of the digits must have a 1 or a 0. Okay. So each of the digits must have a 1 or a 0. And how can we count this? So we remove the only digit that does not have a 1 or a 0. So that's the digits like 22222. Okay. So that's the only digit that does not have a 1 or a 0. So this way, we have, so so this implies, so when we remove the only digit that does not have a 1 or a 0, there's only one possible digit. So it's like 222 in n places. So there's only one digit like that. So we calculate the total, 2 times 3 to the power of n minus 1. We've already done that. Minus 1. Okay, so we subtract 1. And we have that this is equal to 2 times 3 to the power of n minus 1 plus 2 times 3 to the power of, so the size of n0, so this should be minus 2 to the power of n. Okay, so that's this. Then this is plus 2 times 3 to the power of n minus 1 minus 2 to the power of n minus 1. And then we have minus n0 intersect n1. Okay, so let me scroll down a bit. Let's simplify this. So we can, let me change my color. So we can cancel this out and let's see what we can get. So we have that. So let me take this to the other side. This is equal to, so we have 2 times 3 to the power of n minus 1 minus 2n minus 2 to the power of n minus 1 minus, so okay, this so I've accounted for this, accounted for this, accounted for this. So this becomes plus 1. Okay, so can simplify this further. So 2 times 3 to the power of n minus 1. So 2 to the power of n minus 2 to the power of n minus 1, this can be seen as minus 3 to the power of, so minus 3 times, rather, minus 3 times 2 to the power of n minus 1. Okay, so it's 1. Okay, so let me scroll back up, or let me put it somewhere here. So let me write it, let me see if I can write it in a green color. Okay, so we have n0 intersects n1. This is equal to 2 times 3 to the power of n minus 1 minus 3 times 2 to the power of n minus 1 plus 1. Okay, so let's just check that everything checks. Mhm. Yeah, okay. So, and in fact, analogously, because the sets n1 and n2, behave similarly. So in fact, we have n2 intersect. So this is going to be the same thing. So let me erase this. Okay. So next we need to find, So next we need to find this one. So N1 intersect N2. Okay. So let me scroll down. So we want to find, scroll down and do it. I want to find N1 intersect N2. So by inclusion exclusion principle is equal to N1 plus N2 minus N1 intersect N2. So N1 intersect N2. So it means we want to count the numbers that have at least a 1 or a 2. Okay. So the numbers that have at least a 1 or a 2 is actually every number because the first digit must either be a 1 or a 2. So it must be 1 or 2. So it can't start with 0. Okay, so basically it's every number. So this is actually going to just be 2 times 3 to the power of n minus 1. Okay. So sorry, this should be union. So union. Okay. And then we want to find, so we've already calculated the total n1 and n2. So that was 2 times 3 to the power of n minus 1 minus 2 to the power of n minus 1 plus 2 times 3 to the power of n minus 1 minus 2 to the power of n minus 1. Okay. Minus n1 intersect n2. Okay. Precise. So let's simplify this. So we can cancel this out. Okay. And we have n1 intersect n2 is equal to, so we can take this to the side. Then we have 2 times 3 to the power of n minus 1. Then we just have minus 2 to the power of n. Yeah, I think that's it. So this and this gives minus 2 to the power of n. Okay, so you just that'll be like minus 2 times 2 to the power of n minus 1, and that's about 2 to the power of n. Okay, so we can bring this here. So let me erase some things. Let me write it with this color. So basically we have that n1 intersect n2 is equal to 2 times 3 to the power of n minus 1 minus 2 to the power of n. Okay, so let me erase this. Okay. So now let's find what we, want to find. Okay. So this last term is what we want to find out, and that's why we've, done most of this. So let's plug in what we have into the equation and see. So this equation I'm asterisking. So I'll just plug it in directly. We have 2 times 3 to the power of n minus 1. This is equal to, okay, so we have n0 is going to be 2 times 3 to the power of n minus 1 minus 2 to the power of n plus 2 times 3 to the power of n minus 1 minus 2 to the power of n minus 1 plus 2 times 3 to the power of n minus 1 minus 2 to the power of n minus 1 and then minus, so n0 intercept n, so it's going to be minus 2 times 3 to the power of n minus 1. So I'm writing this here, okay? So that's minus 3 times 2 to the power of n minus 1 will change to plus 3 times 2 to the power of n minus 1 minus 1. And then n1 intersect n2. So let me write it on a new line. So minus 2 times 3 to the power of n minus 1 plus 2 to the power of n And then this other one, so minus 2 times 3 to the power of n minus 1 plus 3 times 2 to the power of n minus 1 minus 1, and then plus the term we're looking for at the moment. Okay, so let's try to simplify things. So this guy goes what? These two cancel each other. So I think this and this cancel out. Mhm. This and this cancel out. Mhm. Okay, so let's be careful that we're not making a mistake. Okay, yeah. So 3 times 2 to the power of okay. So let me scroll down a bit. So we're left with okay, this and this cancel out. Mm-hmm. And what else we have? Okay, so minus 2 to the power of n minus 1. So we have this, this. Okay, so let's write down let's write out what we have. So we have 0 equals to have minus 2 to the power of n minus 1 minus 2 to the power of n minus 1 plus 3 times 2 to the power of n minus 1. Wow, lots of algebra going on here, so you have to be careful not to make any mistake. Minus 1 minus 2 times 3 to the power of n minus 1 plus 3 times 2 to the power of n minus 1 minus 1 plus this. Okay, so let's simplify this. So these first two terms can simplify them to be minus 2 to the power of n. Okay, because it's just like you're multiplying by 2. And okay, let's look at it this way. So we have this, we have 3 times, and then we're subtracting it twice. So like this 3 times here simplifies to 3 minus 2 into 2 to the times 2 to the power of n minus 1. Okay, so this will just be 3 minus 2 is 1. Okay, so those 3 times simplify to this. Then have minus 1, so minus 2. Okay, and then we have minus 2 times 3 to the power of 1. Okay, so let's see. So 2 to the power of n minus 1. So actually, this then 2 to the power of n minus 1 plus 3 times 2 to the power of n minus 1. This is going to be 4 times 2 to the power of n minus 1, which is 2 to the power of n minus 1 plus 2. So this will be, so I can simplify this to plus 1. Okay, so, and let's see, and then we have minus 2 times 3 to the power of n minus 1. Okay, so because we want to take this to the other side of the equality, so let me change this to, let me just swap it. So this is going to be 2 times 3 to the power of n minus 1. So I'm just, multiplying by minus 1 plus 2 minus 2 to the power of n plus 1 is equal to this set. intercept N2. Okay. So we have the set and we want from 1 to 1 million. Okay. Okay. So first of all, 1 million does not satisfy what we're looking for. Okay. So it means we want up to, so let me just put 99. Okay, sorry, not 99. By working in base 3. So that'll be 2, 2, 2, 2, 2, 2. Okay. And of course, for the number to have each at least each of the digits appearing once, it must be a three-digit number. So it means we have to start from 1, 0, 0. So basically, to solve this, we're going to sum this. Okay, so from n equals 3 to n equals 6. Okay, so we're going to sum this. So let's sum it up. So we have 2 times 3 to the power of n minus 1 plus 2 minus 2 to the power of n plus 1. Okay. So we have sigma from n equals 3 to 6. Okay. So to sum this from n equals 3 to 6, I think we can do this manually. So this is going to be 2 times. So when n is 3, that'll be 2 squared plus 2 into. So this is going to be 4. Okay. So let me scroll down. I need enough space to do this. Okay, so plus 2 times 3 plus that should be 5. 2 times 3 to the power of 4 plus 2 minus 2 to the power of 6. I will have 2 times 3 to the power of 5 plus 2 minus 2 to the power of 7. Okay, so this is 3, 4, 5, 6. Yeah. So this here is going to be equals to, so this 2 times 9. So that's 18 plus 2 minus, so 2 to the power of 4 is 16. So 18 minus 16, that is 2, plus 2, that is equals to 4. Okay. This here is going to be, so this 2 times 3 to the power of 3, that's 27, 54, plus 2 minus 32. Okay, so 54 minus 32, that is going to be 22 plus 2, so 24. Okay. And for this we have 2 times 3 to the power of 4, so it's 81 times 2, 162, plus 2 minus 64. Okay, so 162 minus 64, that is going to be 98, plus 2, that's going to be 100. Okay. For this last one, so 3 to the power of 5, that'll be 243 times 2, that'll be 486. Okay, so plus 2 minus 128. So 486 minus so 486 plus 2, that is 488, minus 128, that's going to be, so it's going to be equal to 360. So when you add this, so 4 plus 24, that will be 28 plus 100, 128 plus 360, that is 488. Okay, so the final answer is 488. And let's scroll up. So this is that is option A. So 488. Hope you enjoyed the video. Please don't forget to share, like, comment, and subscribe. This was quite a difficult counting problem, and yeah. If you stay to the end, thank you. And see you in the next video. Goodbye. Cheers.